Okay, so today we're going to be covering diffusion models. Have you heard of diffusion models before?
I've only
Maybe
heard the word about it.
have you heard of like stable diffusion, Dolly? Maybe. Okay. Uh, I think have you ever seen like ChatGPT generating images? I
Yeah.
think they're diffusion based. So far, what we've covered in terms of generative modeling, and again, in our case, we're talking about generating images. So sequential models like RNNs, LSTMs, I will no longer be addressing you only, Seth. All right. So transformers, LSTMs, RNNs, I'm not really considering those generative, right? Um, if you could generate an image, I'm calling it generative. So we've only covered VAEs or variational autoencoders and generative adversarial networks, right? GANs. So that was last lecture. And so we'll be covering like the last one, diffusion models. But before that, let's kind of do a brief review of kind of like the framework to view generative modeling in general. So again, this is a bit of review from the GANs lecture, but again, okay, so let's define like image space, right? In literature, it might be just called like the image domain, right? And so again, this is just all conceivable possible images that could exist, right? So really the easiest way of putting it is all possible combinations of pixel values, right? For some dimension of images. So for example, if we have a 10 by 24 like resolution, right? And we have RGB, so that's 1024 by 1024 by 3. So that's a total of, over 3 million dimensions, right? So in this case, like each dimension corresponds to a single like RGB value, right? To a single like, yeah, Roy G bib value that can be, no, sorry, RGB value that can be modified. So you can imagine we're working in a extremely, extremely high dimensional space, right? So directly optimizing the space is oftentimes a pain, right? But we'll get into how to work with that in a little bit. So when it comes to generative modeling, we want our model to generate like some subspace of image space, right? In this case, again, like we're really working like over 3 million dimensions, right? So this is just a very crude 2D representation of this very high dimensional space. But just kind of humorous example, if we kind of carved out like an image space, like the set of images that we want, right? So in this case, we want our generator to only generate images of cats, right? So keep in mind, this graphic could be fairly misleading. Uh, like it doesn't have to be like fully connected. You could have like disjointed spaces, like disjointed regions, right? But they don't necessarily have to be fully continuous either, right? For now, we'll be making those assumptions for simplicity.
So like would the image space be represented as like one image and then like the image to the right of it would be like or like to the right of it obviously it's like way too many images to really represent it like that, but like the image to the right would be like you change one pixel, like you change
Exactly.
one pixel.
Exactly. Yeah. So an image, so like another image in one direction would be that image but modified by 1 pixel.
Okay.
Yeah. That's good insight. I should have a graphic for that for next year. Okay. So again, it's very difficult to work or even conceptualize these high dimensional spaces. So we oftentimes represent them with probability distributions, right? Where we have a positive probability at any image. So again, the x-axis is all conceivable images. We have a positive value at any image we would want our model to generate, right? So in this case, if I sub cat is just all conceivable images of cats, we would want a positive probability value of everywhere there's a cat. And again, the reason why it's some positive value is that all of these probabilities must sum to 1, right? As opposed to, because that's the rule of probability distribution, right? And they all have to be non-negative, right? So the rule of probability distribution, they have to sum to 1. And second, they all have to be non-negative. We're just doing a brief review of the GAN stuff if you guys were here for last week. If not, don't worry about it. Going fairly slow. So again, if this probability distribution is all possible images we can generate, we want p theta, which is the probability distribution of what our model can generate, to literally equal this. Right? We want them to be the exact same. Does that make sense so far? Okay. So let's so again, working directly in image space has been a huge challenge, especially like pre-2015, right? So what people often do is instead work in latent space, right? So imagine latent space as a significantly lower dimensional space, right? So if image space is what, like over 3 million dimensions, latent space is oftentimes just 100 dimensions, fewer than 100 dimensions, something like that. In our case, we're just saying it could just be 2 dimensions, right? Um, So what we want to do is we do all of our optimizations. So like, the input to our neural network or like any, gradients, any loss functions we calculate all of our optimizations are done in latent space, right? Because again, it's easier to optimize. But we're assuming there exists some, a bijection or isomorphism between, okay, if we have an image in image space, that corresponds to a unique vector in latent space, right? And we can go from latent space back to image space, back and forth. So that kind of function that lets us do that is oftentimes a neural network, right? And so because neural networks, aren't always perfect, we theoretically can assume it's like a bijection. We can go from one to another and back, like without any like loss per se. But that's a fairly big assumption. Oftentimes it's not a perfect bijection. Okay. So variational autoencoders. Okay. So both GANs and variational autoencoders make this assumption of, okay, we take our image and we move to latent space and we do our optimizations latent space, right? They approach it in two like theoretically different ways. And again, I'm not really going to be talking about the architectures of the models. So the way variational autoencoders do it is, okay, so again, our entire cat space, so again, the subspace of images that like only consists of cats, again, these are the images we want to generate. We obviously can't sample from like all conceivable images of cats. So what we do is we try to estimate this image space that we care about with our data set of cats, right? So we try to estimate all cat images with just, say 100 cats, right? So what we do is we try to make a mapping. We try to learn this mapping from a image of a cat to a region in latent space, right? So notice it's a region in latent space as opposed to a single latent representation vector, like it is in this case. In this case, we're mapping a single image to a single vector in latent space. In this case, we're for VAEs, we're mapping an entire region. So at first, we're just, when we start with the untrained model, we're really just mapping like random areas in latent space to an image of a cat. But to make this for the latent space to be useful for us over time, like while we train, we want all of these regions. It might be a little bit hard to see because it's kind of low contrast, but they're all kind of clustered together in the center, right? So that way, if we want a new image of a cat, we just sample from one of these filled in regions, and that will correspond to a new image back in latent space. And again, we're sampling a vector that we've never seen before during training. Does this kind of idea make sense? So again, if we, with variational autoencoders, we're kind of hoping we have enough overlapping regions and we have enough of these regions to fill up enough of latent space. Like if I were to sample from some corner here that never was encompassed by some region, then I'm going to get garbage on the other side, right? Okay. So GANs approach filling up latent space in a different way. So instead of starting with an image and mapping it to some region, we start in latent space. And again, we start in the center of latent space. So again, think of like the mean of latent space, like in our case, like 0, 0. They all start somewhere near 0, 0. And we map those latent representation vectors, and we try to assign them to images in image space, right? So GANs have a generator and they have a generator model and a critic model, right? So what the generator model does is it's what's trying to map a random latent space vector to an actual image. And the critic model tells us, okay, did you do a good job? Is the image you just generated, in this case, like, it's generating random noise, does that belong in the image space, right? And so we keep, we're still sampling roughly the same vectors during training, but the point is they slowly point closer and closer to image space until they will point within image space. And then that way, once we sample a arbitrary vector in latent space, we're almost guaranteed that that maps to a new image we've never seen before in image space. Do these mappings kind of make sense? They're kind of working opposite directions conceptually. Okay. So the big thing with diffusion models, or at least classic diffusion models, is they're working entirely in image space. So conceptually, it's a very big jump, right? Later on, at the very end, we'll cover a diffusion model that kind of works with latent space for just to work more efficiently. But the classic diffusion model doesn't really rely on that. So what we're doing instead is, instead of starting from a latent space vector and mapping it to an image, right? Or like sampling an image space vector, a latent space vector, and then using a neural network to go from that to an image, we start with some noise, like literally the image of noise. So in like like literally like a image of noise, right? And then we go from that, we learn a pathway, quote unquote, that goes from that image of noise, and then we kind of learn and navigate our way back into image space, right? Okay, so what exactly does that mean? Well, again, if we start, so yeah, so diffusion models have two processes. They have the noising process. In literature, that's also often called the forward process. They have the denoising process. That's often called the backwards process. I'll just be calling it denoising and noising because I don't want to mix it up with like forward and back prop, right? So in the noising process, we start with an image, again, from our data set that we know is an image space. And then over like a few iterations, so in this case, 5 iterations, but in reality, you're doing like thousands of iterations, right? So over thousands of iterations, you slowly add more and more noise, right? So like noise is literally like Gaussian noise, right? Like static you might see like on your TV. So as you can see, as we kind of add noise to our image, it looks less and less like a dog, right? So as we're on this border, like you can barely make out that's a dog, right? And then we keep adding noise until we're like completely away from dog space.
If the model is like, it wouldn't know how to know like what a dog is yet, so how would it know when it's like done noising?
Yeah, it just takes a number of steps.
Oh, okay, so that's like the parameters.
Yeah, so there's a scheduler we follow, right? Where I go over the math for it at the end, or I'll just cut to it right now. It's guaranteed that by the end of the number of time steps, you go to full noise. So you can think of like in the beginning, um, it's like a weighted sum. So at the end, you're weighting noise like more than you are weighting the original image. So at your last time step, your image is like 0.99999% image or noise, like 0.00001% original dog image. Does that make sense?
So you could do like a really small number, but it would.
Yeah, you could, yeah.
Less effective.
Yeah, exactly. You could. It hurts the model's training, but you could.
Yeah.
And again, when we add noise, we just kind of do this just by we do not use a machine learning model for this, right? Because again, it's pretty easy to just grab noise and add it to an image. We could just grab some random thing static and add it to an image. So once we do this noising process and we know each of these steps, we then use a machine learning model, so the diffusion model, to learn to retrace our steps, right? So for example, if at t equals 4, right, this is what our image looked like. We start at t equals 5, so pure noise at the denoising step, and then we try to predict t equals 4. And from 4, we try to predict 3, from 3, we try to predict 2, and so on and so forth, right? So the idea is that, okay, if we just, we want to learn like from as many different starting points as possible, so as many different, random combinations of noise, and for each combination, as many pathways as possible, right? So you'll see later on, like there isn't a single pathway of going from noise to the image. There's a lot of different pathways you can take. So the idea is if we learn from a bunch of different starting points and a bunch of different pathways, then we've learned like a very robust, like a very generalized approach. Okay. Okay. So again, what does it really mean to add noise? Again, this is a bit of a simplification, but the idea is it's a weighted sum between the actual image, like the original image from your data set. You sample like the image of noise from a Gaussian distribution, and then you're left with a somewhat more noised image. And so in the denoising step, you start with that noised image, and then you try to predict how much noise was added at that time step, and then you try to subtract it to get your less noise image. So again, for denoising, you're actually predicting how much noise was added at that time step, and then you subtract it. So adding and subtracting noise is it's added. Sorry, adding noise to your image is additive. Like it's literally additive and subtractive, right? You're not really multiplying or transforming your image in some nonlinear way to make it noisy. You're just literally adding noise. Does that make sense? Okay. So if you were kind of track the progression of the image from t equals 0 to all the way at the end, so Seth, you'll see that like you start from an image and over time it gets more and more staticky, and then the reverse process, you start from noise, and then over time at each reverse time step. So by the time you get t equals 0, the hope is to have fully gotten this image of the dog back. Okay, so again, what does it actually mean to sample an image from noise? So for this low dimensional image, I think what's maybe like 10 by 10, each pixel, each RGB value is literally sampled from the normal distribution, right? So again, like if I say my normal distribution is like 0.5, right? Or the median is 0.5, then I just sample each of my RGB values from that. And so I do that for every single pixel. And that's what it means to sample something from noise. Okay. So notation wise, we're not actually setting the mean to 0.5. In the diffusion paper, the mean is at 0, and the standard deviation, or sorry, the variance is like 1 effectively. The identity matrix, which is effectively 1 for high dimensional spaces. Yeah. So again, like I always had 0.5 because this like they never have negative pixel values, but they have some mapping between, you know, like -2 to +2 that goes from 0 to 255. Does that make sense? So whenever we have the notation of sampling epsilon from the normal distribution, we mean sampling a Gauss, like an image, some n by n by 3 image from noise, basically. So just remember that epsilon being corresponding to a specific image of noise. Any questions about this? Because I'm just gonna be assuming you guys are good at this moving forward. Okay, perfect. Okay, so I'm just gonna jump straight into the architecture before covering the objective diffusion, because I think that intuition is good enough for understanding the architecture. So diffusion models, almost pretty much all of them use the unit architecture. And so that's kind of the go-to when dealing, we're going from image to image. The idea is, again, you input the image. So again, this is for the denoising step. You input the image and you get out how much noise is from that image, right? So you're predicting, okay, how much noise was added to this image, and that's what you're trying to get out. And so it follows the encoder decoder structure. So the orange section are the encoding steps or the downsampling steps, where we break down our high dimensional image, and then we shrink it down to a small lane representation. And then we have a upsampling, like, or the decoder steps, where we project that back up into a large high dimensional image. Again, I know it's a little confusing because we don't use lane representations. We're not like this lane representation is only used for the sake of producing, like, predicting noise. We're not really optimizing it the same way we would optimize, like we never calculate the gradient with respect to the loss for this lane representation, right? Beyond just training a good encoder decoder. Okay. Yeah. So I'm just going to break down how this works. So first, residual connections, right? So again, this is just how residual connections work in general. So for a normal neural network, right? This, if you're just imagine neural network has like some function at big F, well, it's the weights times the weights at that layer. So layer L plus 1 times the input at that layer, X of L, plus the bias at that layer, right? Everyone good with this notation? Remember how that works? Okay. And so, yeah, so just some notation I'll be using. And then if we try to take the gradient at some point during a loss function of the original input with respect to the output of that layer, we get this long chain, right? Does everyone kind of remember this from just how backpropagation works? Okay, I'll assume that is yes. Okay, so you may imagine though, as our model gets extremely deep, right? Like we have like a bunch of layers. Well, this chain gets extremely long, right? So if you assume that most of the outputs of our layers, like the gradients for them, so the gradient of x of L with respect to L minus 1, so on and so forth, if most of those are less than 1, right? Like even 0.95, for example, right? Well, if we have like, maybe 100 layers or 1,000 layers, which is very feasible for like large language models, right? Our gradients are going to vanish to 0, right? And if our gradients are 0, our model is not going to learn. Alternatively, like we could just have a couple of gradients in this long chain that are close to 0 or 0, right? And that will also just cause our entire gradient to vanish, right? And so what does it really mean for the magnitude of a gradient to be very small at some layer, right? Like conceptually, what does that mean? Well, that means like our layer, so like layer 1, for example, isn't really modifying the output very much, right? So the input we're taking in and the output from layer 1, it's pretty much the same thing as this original input. Because remember, the gradient is what direction to modify the weights and by how much, right? So the sign of because gradient is like a vector in space, pointing gradient descent. The magnitude tells you how much. So if the gradient is very small, that means that layer hasn't really modified our original input. So in other words, if we have an extremely long, like a very deep model, it's very possible that our model, like some layers just don't contribute much, right? Which is understandable, right? Because if you have like thousands of layers, you're bound to have at least a couple that don't really contribute much to the final output. Problem is those couple end up causing a vanishing gradient. So residual connections kind of give you that freedom to have some layers that effectively learn the identity function or don't transform their input that much without causing a vanishing gradient. So now instead of the output from a given layer just being given by this, it's now a sum of the standard output for that layer plus the original input to that layer, right? So if you kind of look at it visually, we pass the input to the layer as normal, right? And this is the raw output. But then our final output, before we feed it into the next layer, we add in our original input to that layer, right? This is what we're doing, making sense here? All right, take that as a yes. Okay. So yeah, so the output of a given layer is the input plus that deep layer's output, as opposed to just that deep layer's output. And so, again, if we kind of evaluate the gradient, no, I can't see the board. If we try to evaluate the gradient at this, the gradient of a layer's output with respect to its input, it ends up evaluating to the identity matrix plus, the gradient of that layer. Before it was just this right-hand term, which of course could go to could be below 1. And if you chain those all together, we get a vanishing gradient. But because we have this additive identity matrix, our gradients are now at least I, right? And of course, it could be, the gradient could be negative, so it's minus I, but you guys get the point, right? Like the magnitude of the gradient gets boosted up to the identity matrix. So in other words, any layers that learn nothing, right? Their gradients are the identity matrix, so nothing vanishes. So we have the freedom of some layers contributing nothing. Okay, so this just gives us diffusion models in recent years are extremely deep, like just as transformers are. And so what allows us to be that deep is this residual connection. Okay. So the second thing was positional encodings. Does everyone remember how they work, like sinusoidal positional encodings? All right. I saw 2 hands out of 5. So okay. So the way positional encodings work is that so your encoding might be, let's say, d dimensions, right? And again, the purpose of this encoding is that it represents what time step you are at your image, right? So again, like you would imagine that, predicting how much noise has been added to a model is dependent on the time step, obviously, right? But of course, the input to the unit model is just the image, no information about the time. So we need some way of letting the model know, okay, what time step are we at? So we do that through the positional encoding. And so if we have some d-dimensional positional encoding, right? At the early layers, so let's say at dimension 1. Yeah, so at dimension 1, right? By the way, I'm gonna stop messing with the slider. So each of these dots just represent the encoding for time step 1, the encoding for time step 2, so on and so forth, and the first element of their encoding. So we're looking at the first element of time step 1's encoding. So in this case, it's like 1.57, right? So you can visually see, hey, that's pretty close to position 2's encoding, right? Like very, very close, right? So as we increase our dimensions, increase a little bit too fast there. Yeah, so sorry. Yeah. So as for the dimensions that are fairly high, let me increase my D to 100. Okay. Yeah, so for the very high dimensions, right, you can see that time steps that are nearby each other have visually similar positional encodings, right? So again, at dimension 9, there's no 9.3. At dimension 9, time steps 1 and 2 are fairly similar. But for lower time steps, right, you can see that, hey, now time step 1 and 3 have very different positional encodings, right? So what the model is effectively trying to learn is that, okay, positional encodings that are very similar in their lower dimensions correspond to, time steps that are very close together, and positional encodings that are very far apart in these larger dimensions. So again, time step 1 and time step 10, you can see that they're very different at time step or at dimension 7, right? So they correspond to very different time steps. Does that make sense? Again, the model never actually sees like t equals 1, t equals 2, t equals 3. The model only sees these dimension, like these vector embeddies. So, in practice, like, again, we have an entire vector representing the positional encodings for a single word. So bird, for example, this is what 6 dimensions, right? So you can kind of see like each of the dimensions separately. Oh, no, you want to ask a question. Okay. Everyone got on positional encodings? All right. Okay, nice. So just a review. The encoder consists of like pairs of residual blocks that feed into downsampling steps. So we just go from residual block to downsampling to residual block and downsampling and so on and so forth, right? So you can add as many of these pairs as you want. Yeah. And so the residual blocks are effectively just consist of convolutions with a nonlinear activation function and a normalization step. This is just to further stabilize training, further make sure your gradients aren't too big or too small. And then they feed into each other, so on and so forth. Positional encodings, at least I think for like the early diffusion models, you added them to your original vector after like the first couple convolution steps before normalization. I think these are just shown to empirically work. There isn't any more reason to like insert them here as opposed to insert them earlier or later. Okay, and that downsampling, again, the goal is to crunch down that high dimensional image, just a very small lane vector. And so downsampling consists of still convolutions, but now like the window we're sliding across is a lot larger. So now, before these convolutions mostly retain the shape of the input, now we're actively trying to make them smaller. Okay. And so again, we have residual connections going from like within the residual block. So at the beginning of the block to the end of the block. But the output of each encoder's residual block, you can see the skip connection or residual connection, they're interchangeable, connects to the final step of the decoder's process, right? So the decoder also has residual blocks. Again, remember these like retain the size of the image, but they're followed by upsampling steps. So again, to upsample, we have transposed convolutions. I've went over this a few times now, but transposed convolutions are kind of the inverse of CNNs. Not exactly, but you can think of them as that, where the larger your stride is, the larger your output is. Okay. Yeah, so does this make sense? Just a brief unit architecture. Okay, perfect. Okay, so now on to like moving back to just like the objective understanding how diffusion models work, right? So before I just kind of said we just kind of take the image or the noised image at some time step, and then we just add Gaussian noise, but how do we actually add it together? So if x t minus 1 is, so yeah, this is the kind of the recurrence relation between like adding noise at each time step. So for example, if we start at the very first image, x0, right? Again, this is the image straight from our data set, no noise has been added. Well, we add or the next step, like the slightly more noised version, so x of 1, is the weighted sum between square root of 1 minus beta 1 plus 1 plus square root of beta 1, where epsilon, again, is that noise, just that pure Gaussian noise from before, right?
What is beta 1?
That's just some parameter. That's just some hyperparameter we can tune. It goes from 0 to 1, right? So you can think of this x1 as a weighted sum between like, so for example, if beta 1 is like 0.9, right? Then most of our image will consist of noise as opposed to new stuff, right? So let me skip to that.
So you would probably want it pretty low.
Yeah, so you would want beta 1 to like increment very slowly, right? So as you can see, like, so in this case, I skipped a few slides, but alpha is 1 minus beta, right? But regardless, if you have that parameter very high, you jump to a very noisy image very quickly. If you have the parameter very low, you might not even be able to tell the difference between this image and that image, right? So noise has been added, but a very small amount of noise. Okay, but I skipped a few steps. Okay. So yeah, so this is how you would add noise at a single time step. Okay, so if we then consider x2, so if we were to then noise x1, right? Well, if we then substitute in this formula for x1 into the formula for x2, you can then simplify it to get two terms, right? So in red, we have like the term relative to the first image x0, the unnoised image. And then the right-hand side is how much of the Gaussian, like how much of the new Gaussian noise we're adding, right? So notice we've actually sampled from the, like we have two separate noise, like pure noise images, E1 and E2. So we've sampled twice, right? So you can imagine as we keep sampling, right? Like once we're at like X 1000, we'd have ended up sampling like 1,000 pure noise images, right? And these square roots end up being uh like the power of A3 times A2 times A1 and so on and so forth. Now notice like not like notice that these are numbered, like beta, there's beta 1, beta 2, beta 3, and so on and so forth. As we kind of continue like the noising process, we actually like increase beta over time, right? So beta might start off as like 0.2, and the next step we increment to like 0.2001, right? But yeah, okay. So we can simplify this recurrence relation into this formula over here. Again, that doesn't really look too simplified. So we can further simplify this green portion into the square root of 1 minus a bar, where a bar is just the sum, or sorry, the product of each of those alphas. And again, alpha is just 1 minus beta. Like alpha of s is equal to 1 minus beta of s. Honestly, so this is equal to like 1 minus beta at 1 times 1 minus at beta at 2, and so on and so forth. For whatever reason, the paper kind of swaps between using alpha and beta. I think it's just to have like this very nice 1 minus alpha bar notation, right? There's no other reason beyond just for reparameterizing alpha as beta. Okay, so in other words, right, we could represent noising our image in terms of like, okay, from image 1 to image 2, image 2 to image 3, or from a single shot from noising image 0 to like some time step t in like a single process. So notice in this case, if we just noise in a single shot, we only have to sample our noise epsilon a single time. And that's a pretty cool property of normal distributions. Okay, so again, both of these are equivalents. The one at the bottom is what's preferred just because it's a lot more efficient. You can just go from time step 1000 to 0 to 1000, just a single step. You don't have to keep keeping track of each of those noise steps. But yeah, and I already went over this example of if you have a very high alpha for a given time step, then you retain more of your image, less of its noise. If you have a very low alpha, then you lose most of your image in a single step. Again, we oftentimes don't have an alpha this drastic. Okay, so as I was saying earlier, our alphas are numbered, right? So alpha is dependent on time. Like we're not using the same exact alpha for every time step. So we can either have a linear schedule or a cosine scheduler. So I know these formulas are kind of hairy. You can just kind of look at their values on this right-hand side. So in this case, realizing the numbers are very small, but you can see that the y-axis goes from 1, right? So from an alpha value of 1, it'll now go above 1 to an alpha value of 0, right? So you can see that, as we kind of progress, like noising our image, at first for the cosine scheduler, we add very little increments of noise. Oh, like in the early time steps of the cosine schedule, we had very little things of noise. And it's only at the very end that we start adding a lot more noise. Like we don't even reach linear amounts of noise until like roughly the midpoint of noising. The early diffusion paper actually used a linear like noising schedule, like in terms of how much to decrease alpha by. And again, lower alpha means more noise added at a single time step. But you'll notice that like we lose sight of the dog, like really at the middle of the noising process. So from this entire right-hand chunk, there isn't really much we could learn. Like we've already left image space at this point, right? So later papers realized that a cosine scheduler was a lot better, a lot easier for the denoising process to learn. Okay, so that's about it for noising. Any questions about this process, any of the formulas? Okay, perfect. So I'm doing pretty good on time. Okay, so denoising. So again, naively, right, for denoising, or at least surface level, intuitively, you would think that, again, remember, we're trying to retrace our steps, right? So noising, we have our steps to leave image space. Denoising, at every iteration, we're trying to enter image space back, starting from noise. So at image x of t, So a more noise image predicts x of t minus one. So that was like if we're at this image, we want to predict the image that brought us there, x of t, right? So specifically the way we do this is we actually end up predicting, again, we predict the noise that was at that time step. We don't directly predict x of t. I think the earlier diffusion papers attempted to directly predict x of t, but optimization wise, this was a lot simpler, and you'll see why because of the loss function. Okay. And so again, beta is a high parameter, and E of t is what we're trying to predict. So we're given that, so again, we already have x of t, that's our noised image. If we can just predict E of t, we're guaranteed to just go that previous time step, right? But there are some very big drawbacks to this kind of approach of predicting noise at every time step and working our way backwards. So again, this is kind of the visualization we're familiar with, but yeah. So the first one is just the pure amount of storage / compute this would require. So again, if we just consider like a single, just look at this top dot for now, right? We just sample our first x of big T, so some random space and noise. We're trying to work our way back, right? Well, first, remember each image is pretty big, right? 10 by 24 by 10 by 24 by 3. So if we have 1,000 times, 2,000 time steps, which again, the diffusion papers had around 2,000 time steps, sometimes more than that. Well, we're storing like 2,000 pairs of image and noise, right? So x of t and the epsilon that was added at that time step, right? That's a total of 4,000 like image-sized things we have to store in memory, right? But remember, like we're not just sampling a single thing in noise and trying to work our way back. To generalize well, we're sampling multiple starting points, right? So if we just, it's very conceivable to just try to sample maybe 100 random spots of noise to work our way back to this one image. Well, then we end up trying to store 40,000 images like in memory when trying to denoise a single image, like during training. That's a very big computational cost, right? For a single image, that's a very big computational cost. But let's say, you're very good at like hardware optimizations, you're able to somehow make that work, right? Another more, I guess, fundamental issue is that when you're kind of floating out here in like noise space, right? And you try to make a small increment from x of t to x of t minus one. So that's, you made a small jump. Well, your image still pretty much looks like noise, right? Like the difference between one time step when you're pretty much at noise to slightly denoised, there's like pretty much no features to learn. Like there's no dog in there, right? There's no semblance of the original dog. So remember, like, when there's like no difference between our input and our output, we are susceptible to a vanishing gradient. Even if we have residual connections, we'll just end up learning the identity function. Like we'll just kind of float around in image space without really kind of making our way back, right? Does that kind of make sense? Like just that intuition of going from noise to pretty much still noise. There aren't any really learnable features here. So our model would struggle a lot to go from this to this and then work our way back to a dog.
So when you eventually like keep going to a point where
Yeah. So the hope is, so for example, if we were kind of on the brink of entering image space, right? So we could still kind of like, if we were somewhere here, right? We could still make out our dog, then it's kind of conceivable for our model to learn, hey, that's a feature of a dog, that's roughly the head. Like the convolutional layers can kind of pick up those features, right? But if we're all the way up here, right, and we stay there for like 100 time steps, there aren't really any features for our model to pick up on. Like there are, like, that there are because the noising step happened, right? But they're so minuscule that, we're kind of just praying our model like picks up to something. It's more realistic that the model just overtrains and fits to noise and just does some random stuff. Does that make sense?
yeah.
Like what would be a easier thing to learn is going from t equals 200 and then comparing that to t equals 0. Because there's a very clear visual difference, right? The model would have a lot easier time learning the difference in noise between these two images compared to the two basically noise images, right? So in other words, we want some way of predicting like the noise from x of 0 to x of t instead of the noise from x of t minus 1 to x of t. somehow using this quantity, so the noise from 0 to t, and using that to predict what t minus 1 is. Right. So before I kind of show this out in equations, here's conceptually what I'm talking about, right? We want our model, right, to predict the noise. Like if we're at t equals to 2000, right? And this is our x0. We want our model to predict this epsilon, so that amount of noise that brought us from here to there, right? Now, as you might expect from t x equals 2000, again, there are no like really, there's no really useful features here, right? However, during training, because we still had those non-diminishing gradients, we'll learn something that kind of resembles something in the image space. Now, it might not actually look like the original dot, because again, we're trying to estimate what x0 is from x equals 2000. That's just what we want to do. Again, it might not be the best estimate, but it's still in the right direction, right? It's not pointing in some random zone in noise, right? But we're guaranteed to at least move in the generally correct direction. Okay, so we then take that step, and let's say we take 100 steps in that direction. We're now at 1900. Again, from our perspective, there isn't really much to know. But the hope is we can learn a slightly better approximation of x0, right? So you can see that our approximation of x0 is now closer to image space, right? So again, it's still pointing to that approximation. It's not pointing directly to the x0, but as we kind of move on, we're getting closer until our approximation becomes what x0 actually was, right? So we would keep, from x equals 500. So the assumption is by x equals 1, or sorry, from time step 1, we're pretty much pointing at the original image. Okay. Does that intuition really make sense? Okay. And again, remember our arrows are the amount of noise we add or subtract. Okay. Okay, back to equations, yay. But again, we've seen these top two before, right? The first one is how to go from xt minus 1 to x of t from the noising step. And the second one is equivalently the same thing, but it's just in terms of how to go from x0 to x of t, right? These are the same equations, but this one's more important, right? Because remember, we want this x of 0, we want this e theta. That's the difference in noise between x of t and x of 0, and use that to figure out where x of t minus 1 is. Okay, so the actual derivation of expressing x of t minus 1 in terms of this e theta, and again, e theta is the difference in noise between the estimated x and the x of t that we're currently at. I know there's a lot of e's going around, right? But essentially, like if you solve for e for this second equation, and then plug that in and do a lot of math optimizations, you get to this formula, right? Where on the red section, right? Effectively, what we're doing is we're taking x of t, right, our current noised image, and then we're subtracting some scaled factor of noise, right, and then scaling that down further. So in other words, we're taking our noise image and subtracting the amount of noise. Now, the reason why we have these particular coefficients in general is just from working backwards with this equation, like we obtain these coefficients by solving for x of t minus 1 in terms of e of theta. Does that make so? If you were to go through this math, and I can link the paper if you're interested in the derivations, but you would obtain this equation. Does that make sense? Okay, perfect. Okay, so you might be asking, okay, what is the second epsilon term, right? Because again, well, I'll say it once again, e theta is the predicted noise between x of 0 and x of t. This epsilon is a completely new randomly sampled epsilon, right? So in other words, we're kind of hijacking our arrows and making them point in the slightly wrong, like we're making our arrows noisy. Why would we ever want to do that? Well, there is a type of diffusion model, like there was some papers released on just using this term in red, right? So in this case, your pathways would always be deterministic, right? So if you started at some x of t noise, so you always started there, you'd always have learned the exact same pathway from x of t to x of 0, right? Because again, this is deterministic, right? E theta is learned from your model. You assume your model will always predict output the same thing given the same inputs. Now we have this beta epsilon term, again, epsilon just being a completely new randomly sampled noise image. And we have this, so our model kind of learns to different pathways. So this forced some stochasticity, and we learned some different pathways to navigate back to X0, right? So it's forcing us to traverse more of our noise space. So it's just better for generalization in general. Again, you could fully train the model with just the section in red, but it just performs worse for generating novel images. Okay, does this kind of makes this intuition make sense? Denoising and denoising. Okay, perfect. So, so just a review once again. Noising, there's no deep learning involved. We use a schedule. So again, we fluctuate that alpha or beta value. Again, they're interchangeable really, to add noise gradually from from x of 0 to x of 1, so on and so forth. For denoising, we work our way backwards, starting from x of t, and use a neural network to predict the noise from epsilon, or sorry, predict the noise from time sub 0 to time sub t. And then we use that epsilon to work our way to t minus 1. So a little bit of an indirect way of going about it. Okay, so the loss function. So again, this is why we're predicting the loss that was added as opposed to directly predicting like the previous image, because our loss just ends up being this simple, right? So it's the true, so epsilon in this case is like the ground truth. So the actual noise that's added between x of 0 and x of t. So in this case, epsilon would be the, epsilon in this case, the ground truth would be an arrow pointing straight at x of 0, right? And if theta is again our predicted error or the predicted amount of noise that we thought was added, and we just take the mean squared error, right? You might be kind of weirded out by this notation if you haven't taken prob before, but this is the expectation. And expectation is basically saying like, if you sample over all input images, so all possible x of zeros, take the average mean squared errors. So of course, there's some other variables beyond this. So we also uniformly sample like different t values. So again, it actually turns out that we don't actually have to train on every single time step t. So if you have 2,000 time steps, we don't actually have to learn from t minus 1 to t minus 2, so on and so forth. We could actually just sample some smaller number of that and still learn a very strong pathway back to our original image space. You could sample every single t, right? You just don't have to. Yeah, so uniformly sample means every single t has an equally likely probability of being chosen. Okay. And okay, is everyone clear about how this loss function works? Mean squared error between the actual noise from 0 to t and the predicted noise from 0 to t. Okay, perfect. And this is just another visualization. So again, our unit model, the input to the model itself, like the first input layer, only takes an image as an input, but it still takes, we still use the time steps, so in this case 551, for those positional encodings. And so the unit model outputs e theta, and the loss is the mean squared error between the actual noise, epsilon, and e theta. And visually, we can't really tell the difference, but the model can. Okay. And this is just the rough training example, but I've pretty much kind of gone over how this works. So this is just more for your use case. And okay, so earlier I was making the claim that, okay, the classic diffusion model just samples something in noise and learns the pathway from noise to an image, right? So latent diffusion models, which are, I think, proposed. So I've pretty much been talking about the architecture of DDPM, which is a paper proposed in 2020. I think in 2021, latent diffusion models were proposed, literally a year afterwards, where, okay, they decide to train an autoencoder, not the unit model, a separate autoencoder that just converts a image into a latent representation, right? So we learned how to go from image to latent representation and back. And so the why we would do this is we do all of our noising and denoising in latent space. And that's the key contribution. Instead of doing our noising, denoising in image space, which again is still very high dimensional, we do it in latent space. I think they didn't have too many performance improvements. They did have it in some regards, but the key thing here is computational speed, right? Adding noise and learning noise in a 100-dimensional space is significantly faster than doing the same thing in a 3 million dimensional space. Okay, so again, this is a review of how autoencoders work. As you can see, it kind of resembles the unit architecture. The goal, in this case, what we really care about is for the encoder to map an image to this latent space, and then for the decoder to map our latent representation back to image space. So in this case, the autoencoder's objective is learning the identity, right? It's trying to learn the bare amount of features. So again, each feature is represented by dimension and latent space. So the bare amount of features that it needs to remember to reconstruct the image, And if it can do that, if it's only learned 5 features or 5 dimensions, then those 5 dimensions is the minimum number of dimensions we need for our latent space stuff to work. Okay, do latent diffusion models kind of conceptually make sense? All other, like, the loss functions are the exact same, right? I'm not sure if you can make it out from back there, but z of t, the only difference is instead of x of t, so our model takes the image as input, it takes the latent vector, so a vector in latent space as input. Only difference, yeah.
So this is kind of like more of a conceptual question for diffusion in
Yeah,
general.
yeah.
But, like, how, because you can't obviously guarantee that like all the dogs are gonna be like clustered.
Exactly.
So how do you prevent it from like if it's learning how to get to like this dog and this dog and this dog and this dog?
Yeah.
How do you prevent it from just like learning to get to like the middle of all the dogs?
That's a very good question. So that's mode collapse, right? So GANs suffer from that. The answer is it's fairly simple. It's that one, that diversity term helps a lot, because again, you're forcing it. If you take a different pathway, you'll probably end up in a different area in lane space, or sorry, in dog space, right? And the second is that we kind of stop denoising, like, once we've entered dog space, if that makes sense, right? So once we have the image of a dog, we kind of stop, as opposed to, like, on inference at least, right? As opposed to you're trying to reconstruct an image from a data set on inference, if that makes sense. I only had one slide, but damn. I think it turns off that one. Well, I only have one slide. But it's just a comparison of GANs, VAEs, and diffusion models. Oh, sorry, Seth, did that answer your question?
I'm a little confused on your second.
Which was,
You were saying about the data set.
oh, right.
'Cause I understand the like diversity from the.
Yeah, that's like that was kind of my intuition of it. The second part, the diversity term is like the strict answer. Yeah. If you didn't have that diversity term, I think early diffusion models show that they did suffer from mode collapse. They did end up pointing to pretty much the same image.
Okay.
Yeah. Okay, so this is a kind of a big table of just comparing them. You don't have to read through it. I'll just kind of state it outright. So in terms of efficiency, so I kind of classified efficiency in 2 ways. So on inference, how fast can you generate an image? And during training, how efficiently can you train? So in terms of just generation, GANs and VAEs are the best, because you just pass them once you just input your latent vector into your decoder, or sorry, into your generator of your GAN once, and then out comes an image. Right? Just one call of your neural network. Same thing for variational autoencoders. For diffusion models, if you have 2,000 steps, that's 2,000 separate calls of your diffusion model, right? For training, however, in terms of training efficiency, GANs tend to be very computationally expensive, because remember, we're actually optimizing 2 models, right? And they're playing that min-max game against each other. So if you don't remember that, don't worry about it. GANs consists of 2 models, though, and we're training them both together. So that kind of takes a minute. VAEs are very lightweight in terms of training. Diffusion models are very computationally heavy for the same reason of we're learning for a bunch of time steps. In terms of ease of training, so that really just means, are there any significant or famous challenges, and how stable are like our gradients? How likely are we to learn images? How likely are we to converge? So GANs is the worst of these 3 to train, right? Of course, there have been more optimizations that have come out since 2014, like a ton of them, right? But still, GANs still suffer from mode collapse unless you explicitly go out of your way to implement some algorithm. And again, mode collapse is when your generator just keeps generating the same image over and over again. And GANs theoretically can just not converge. Like, it's very possible for GANs to just not converge. And just require a ton of tuning and practice. VAEs, This is like you have to tune like their loss is in two parts. If you remember the KL divergence, if you remember what that is, plus the reconstruction loss. So tuning that requires some work, but it's not that bad. Diffusion models, this is just a computational thing. The key differentiator between why people like diffusion models have like exploded in recent years, because again, uh, they were proposed in 2015, but people didn't really start using them until 2020. The reason why they've exploded in these last 5 years is because of how easy they are to train. They just have that one mean squared error loss, and then it's pretty much it. It's a very, very simple objective. So training is very stable for uh, diffusion models, whereas it's very unstable for GANs. You have to go out of your way to like add a bunch of optimizations, and even then, it might not work. So again, when GANs do work, like when they do converge, you get some very, very good images, like really strong images. The current baselines in terms of not baseline, current leaderboards in terms of like image generation are dominated between GANs and diffusion models, right? So when GANs do converge, they perform very well. It just is very hard to get them to that point. Diffusion models in the last 5 years have just performed very, very well. VAEs, I haven't been talking about them too much for the sole purpose of they're easy to train, they're pretty efficient, they just don't perform very well. A common output of diffusion models is that they just end up being very blurry, or they end up just looking like a weird mesh of two different images, like almost overlap together. So in recent years, VAEs have kind of lost prominence. I mean, there are still some big ones, but GANs and diffusion models are the heavy hitters. The diffusion models being exceptionally easy to work with. So most people think, myself included, that diffusion models are kind of the future for generation in general. Okay, so that's it for today's lecture. I'm going to stop recording, but if anyone has any questions, feel free to stay behind and ask. Otherwise, thank you for your time. Um, I guess I was going to ask one more thing. So next week we will be covering so